Hi everyone, welcome to the second of this week's mini sessions in which I will start to reintroduce regression. So what have we covered so far in the past couple of weeks? Well, we've looked at the analysis options that you have if your studies involve continuously measured dependent variables and categorical independent variables. So for instance, if your IV or IVs are all varied between participants, then your options center on factorial or between participants ANOVA. Whereas last time round, we looked at mixed models as a way of analyzing data where at least one of your independent variables is repeated measures. So what options do we have when at least some of our independent variables, in contrast, are continuous as well rather than categorical? Okay. So actually a lot of research in psychology across lots of different areas involves looking at predictors or independent variables that are continuously measured, that are measured rather than categorical or directly manipulated. Okay. And that's for a number of reasons. For lots of different types of research, it's just not possible or feasible to directly manipulate an independent variable. That can be for practical or logistical reasons. It's not possible. And it can also be for ethical reasons as well, where it's not ethical to directly intervene in a particular variable. So some examples of research questions that you might see in the literature that imply or involve continuously measured independent variables or predictors. So looking, for example, at the theory of planned behavior, one of the most widely cited theories in the whole of psychology, that might suggest that measures of attitudes, our perceived norms about performing a behavior, and the perceived control that we have to perform a behavior will together or each independently predict our intentions to perform a behavior. Similarly, if we're interested in what predicts whether people are willing or unwilling to become an organ donor, some research has looked at whether people's subjective feeling of emotional disgust at the idea of organ donation, the so-called ick factor, predicts that unwillingness. Similarly, somebody's interested in political ideologies, what predicts something like political conservatism, might be interested in whether it can be predicted from demographic factors such as age or sex. So what all of these research questions and potential research designs have in common is that the IVs in each case have to be measured. So for example, people's subjective disgust reactions, or they have to be operationalized in terms of pre-existing categories, such as in the case of participant sex. So in that sense then they're actually, strictly speaking, no longer independent variables in that narrow sense, in the sense that they're not directly manipulated or controlled by the researcher. And in fact, you'll often see them referred to instead as predictor variables rather than independent variables, in the sense that they are hypothesized to predict, in the sense of explaining variance in the dependent variable, or the outcome variable as it's often referred to. For our purposes, I'll use terms like predictor variable or independent variable somewhat interchangeably. Okay. So thinking about, again, research with continuous or measured predictors or independent variables, we'll frequently see, or it's useful to represent our hypotheses or predictions in terms of path diagrams, which summarize the predictive relations that we expect to see amongst the variables. So we might draw out our dependent variable on one side, behavioral intentions in this case. This is from the theory of planned behavior. And on the other side, we have three separate predictors that we want to measure in our participants. And these are each expected to have unique predictive associations or unique predictive effects on behavioral intentions. So when thinking about our research, both in theoretical terms and in practical terms, logistical terms, design terms, when we have measured predictors or using pre-existing categories of a predictor variable, whenever we can't directly manipulate an independent variable, the connection to our design and very good theorizing is absolutely crucial. Okay. And the reason for that is that while we might have very good reason, or we think we've got very good reason to hypothesize that variable A affects variable B. The fact is that if we've only measured both variables rather than directly manipulating variable A, then we still can't be certain that any relationship or association that we observe is causal. Okay, and that's because the association could be because of some other unmeasured factor, a third variable that actually just predicts both A and B. Or there may be a causal relationship, but it could be completely the reverse of what you've supposed. And the statistics themselves cannot tell you anything about the direction, such as to the extent that there is a direction, the direction of the effect. So in practical terms then, what that means is in regression, a significant effect can't in itself distinguish or establish causal relationships between, say, variable A and variable B. So we can't conclude, unless we have a direct manipulation, that A affected B in this context. We can only really talk about associations or talk about relationships in predictive terms in a statistical sense. So we can say something like A predicted B, but we shouldn't be suggesting that A affected or caused B unless we have directly manipulated A. So all of that together means that when it comes to regression analyses with say, measured predictors, the specification and interpretation of a particular model or regression model rests really, really heavily on having good a priori theory-based reasons for specifying your model in particular ways. What are the predictors and what are the outcomes, and why is a causal relationship between them at least plausible? So in terms of reintroducing regression more specifically, what it does is test whether one or more predictor variables predicts, and note not causes necessarily, but predicts in a statistical sense, variation in an outcome variable. So some of the assumptions underlying the analyses that I'll run through in the rest of this session and next week are quite familiar because they are the same as for other parametric stats or tests like analysis of variance. Things like we're assuming normally distributed scores on variables and that participants' observations are independent. There are some other more specific assumptions associated with regression though. The assumption is that in all of the analyses that we're talking about, the association between a predictor, an IV, and a DV, an outcome variable, is linear. Although actually beyond the scope of this lecture series, it is quite possible to test or analyze non-linear relationships as well. Another particular assumption underlying regression is homoscedasticity, which is somewhat similar to the assumption in ANOVA of equality of variances between groups. Again, this is something that hopefully you're relatively familiar with, but yeah, it's an assumption underlying what we are going to discuss for the rest of the session. Okay. So one of the features of regressions is, or regression analyses is, there are many different types or bits of information that you can glean from a particular analysis or bit of output. And the relevance of each of those depends on how exactly you're framing your research question and what precisely it is that you're interested in making inferences about. So yeah, what you look for in the output will depend on what precisely it is that you want to know. So for example, if you're interested specifically in whether a predictor in linear regression significantly predicts a dependent variable, then you might look for the t-statistic and the p-value in the regression output table. You might instead or primarily be interested in the strength and the direction of the predictive relationship, not just is this association significant, but in what direction and to what degree. If you're interested in that, then you will look for the regression coefficients associated with individual predictors. You may also be interested in how much variance in the outcome variable your model actually explains, how much variation in your dependent variable can be explained or attributed to your predictor or predictors. For that, you would look at the R-squared or adjusted R-squared. Then, if you're interested in a regression equation or stating a regression equation that best summarizes the relationship, if you like, the best fitting line, regression line for the data that you have, then the intercept and an individual regression coefficient help you piece together the best fitting regression line equation. Some additional things that are particular to multiple regression are whether, not just whether a predictor significantly predicts an outcome, but whether it does so while controlling for or adjusting for other predictors. Here again, in multiple regression, you would look at the t-statistic and the p-value in the regression table, because that tells you what the predictive relationship is while adjusting for whatever else is in that model. Again, you might be interested in whether the overall model, that combination of predictors, together explains an amount of variance in the outcome that is significantly different from zero, and your overall ANOVA table will tell you that, or the ANOVA output will tell you that. And finally, and this is something that we'll get to in next week's sessions in relation to hierarchical regression, is multiple regression can also tell you something about how much variance in the outcome variable is actually explained by each individual predictor. And that can be signaled or inferred from change in R-squared values between models that either include or don't include an individual predictor. Okay, that will make a little bit more sense when we cover hierarchical regression. So, as I've done each week, I'm going to run through some examples, and to make it as concrete as possible and give you a sense of how your analysis options change as a function of the design and operational decisions that you make in your research, I'm going to start with an overarching research question, look at the simplest sort of possible design that could examine that research question, and then look at how your analysis options change as we build up the complexity of that research question and design. So our overarching question for this time is, let's say we're an organizational psychologist and we're interested in, well, what predicts people's commitment to an organization, their willingness to stick with the organization through thick and thin rather than resign or leave in search of a better job. And particularly this organizational psychologist, or we might be interested in whether people's sense of identification with their organization predicts that commitment. Does our sense of being together as part of one big group in the organization, does that maybe predict greater commitment on our part? So a very simple design that could test that, or a very simply stated hypothesis, might be that, well, stronger organizational identification will predict stronger commitment to the organization. Okay. So we might state it in path diagram terms, a schematic. So we've got our outcome variable commitments, our predictor organizational identification, and suggest that we will see a positive predictive relationship between them. Okay. So as identification goes up, we expect commitment to also go up. We might assess both those through self-report questionnaire measures of both variables, and yeah, that will be the basis of our data. And our analysis options then are simple linear regression. Okay, let's see that in action. I'm just going to go to Jamovi. Okay, here we have our data. The two columns that we're interested here in the first instance are organizational identification and commitment. So a regression analysis can be found under regression and linear regression. Okay, so let's put our model together. So our outcome variable here, our dependent variable, is commitment, and our predictor is identification. So in Jamovi, these boxes differentiate between predictors that are continuously measured, it refers to them as covariates, and predictors that are categorical, which it describes as factors. So identification is a continuous variable, so I'm adding it as a covariate. Okay. Some other things that I would advise you to sort of check or ask for as standard in regression analyses is an F-test for the overall model test, okay, and for the adjusted R-squared as well. I would also ask for the confidence intervals for the estimate and also for the standardized estimate as well. So this is it's often called the beta coefficient. So it is the standardized regression coefficient, okay, in addition to the unstandardized coefficient. All right. So let's look at the output, okay. So first of all, let's look at the R-squared values. So we've got our R-squared and our adjusted R-squared, and that gives us an estimate of the amount of variance explained by our model, by our predictors, in the dependent variable. So of the two, generally go for the adjusted R-squared, especially when it comes to multiple regression, when you've got more than one predictor in your model. In this case, they're stated as a proportion. So basically, in your mind, multiply by 100, and you will get the amount of explained variance in percentage terms. In this model, if we're looking at it at the adjusted R-squared, the model is explaining 39% of the variance in commitment. Okay. The rest of this table gives you the test of the overall model, the significance of the overall model, which is testing whether the amount of variance explained is significantly different from zero. And indeed, it does indeed seem to be the case. And you could write that up as you would for the F ratio from an ANOVA. Okay, that's your F ratio, numerator and denominator degrees of freedom, and your p-value. Looking down at this second table here of the model coefficients, here we have the regression coefficient. So here is the unstandardized estimate, and here is the standardized estimate. So just want to remind you and be very clear about what each of those means. So let's interpret the regression coefficient, the unstandardized coefficient first. So here it is, it's 0.62. So what that means is, and because it's positive, if it was negative, it would be a little bit different. Because it's positive, what this means is that a unit increase in organizational identification is associated with a 0.62 unit increase in commitment in our outcome variable. Okay. If this was a minus 0.62, then it would mean that a unit increase in organizational identification is associated with a 0.62 unit decrease in commitment or outcome variable. Okay, so don't just look at the number per se, but also the sign of the effect too, positive or negative. Now over here we have the standardized regression coefficient. Now that is what the regression coefficient would be if we had first standardized both the predictor and the outcome variable. In other words, if we had transformed them so that they each had a mean of 0 and a standard deviation of 1. Okay. And this can be interpreted now in terms of standard deviations. All right. So what this means is coefficient of 0.63, a beta of 0.63. It suggests that a 1 standard deviation increase in identification is associated with a 0.63 standard deviation increase in commitment. Again, if it was a minus, it would mean a 0.63 standard deviation decrease in commitment. Okay, so the beta coefficient is an indicator of the association in terms of standard deviations, whereas the unstandardized coefficient is an estimate of the association or in terms of the original units of the scales. Okay. Also in this table we have the significance of the individual predictor, so that's our t statistic, and the p-value of that. So highly significant, definitely significant from 0. So this is the whether the slope of the association between identification and commitment is significantly different from 0. Yes, it is. Okay, and if we wanted to piece together the equation for the best fitting regression line, then we can look at the intercept, okay, and the unstandardized coefficient for identification. We can say, well, your best guess for what commitment will be for a given level of identification is this. It will be the identification score times 0.62 plus 1.68. Okay. So at this juncture, I just want to do a quick comparison or compare and contrast of that simple linear regression and a correlation analysis. Now, the key thing I want to point out right from the start is that correlation and simple linear regression are very similar. In fact, de facto, they're virtually identical. What they're both doing is assessing the association between two variables. All right? And the reason why one often gets selected over the other is to do with almost like the a priori theoretical reasons you might have for whether that association is directional or causal. And often we will see correlation used when it's less clear in theoretical terms why one variable might be causing the other. They're just associated rather than having a hypothesized causal relationship. So I'm just going to show you how to do a correlation in Jamovi. So back to our example. Again, it's under slightly counterintuitively, it's under regression. Under regression, go to correlation matrix. And let's select our two variables. So we've got identification and commitment. Move them over here. I'm just going to ask it to flag significant correlations. And there's our correlation matrix. So a couple of things I just want to highlight here. That's the same table from the correlation. And this is the same regression output that I just went through. So a couple of things to highlight. Firstly, that R value is the same as the R value, the Pearson's R, the correlation coefficient, is the same as the standardized, the beta regression coefficient. Because what a correlation is a measure of the covariance if the two variables were standardized. Okay, and again, that's pretty much what in a simple linear regression the beta coefficient is indicating too. Okay, it's the strength of the association between the two variables if they were standardized. Okay. Also equivalent to the Pearson's R correlation is the R from the linear regression, that it's basically the same statistic. All right. And that therefore means that the R squared value that you get in linear regression, a simple linear regression, you could also get from your correlation output. It is simply the R, the Pearson's R, squared. So 0.63 or 0.632 as it happens, squared gives you 0.40. Okay. Again, rather like comparing t-tests and analysis of variance for similar designs, this is just to emphasize that if you have, say, a simple linear regression analysis or correlation, then doing the other analysis is pretty much redundant. You've largely got what you need from one or the other. Okay. Now let's make regression analyses come into their own a little bit more. Let's extend our design a bit, make it a little bit more complex. So now we are hypothesizing not just that stronger identification will predict stronger commitment to an organization, but we're suggesting that will be the case over and above, in other words, controlling for or adjusting for other factors that might also be associated with commitment to the organization. Things like job satisfaction, our annual salary, maybe the more we earn, maybe the more committed we will be to the organization, and maybe demographic factors like age and sex. Again, all of these things might be assessed through self-report measures on a questionnaire. Salary may be measured in terms of annual salary before tax. And representing it schematically, we've got our outcome variable, commitments, and now we've got 5 different predictors to put into our model. We've got identification, but we've also got job satisfaction, salary, age, and sex, each of which will be tested in terms of their predictive relationship with commitments, while adjusting for, controlling for each of the other predictors. So our analysis options here are multiple regression. So that allows us to assess the role of individual predictors in explaining commitments, while firstly adjusting for the role of the other predictors in the model, and secondly assessing the overall fit of the model in terms of explaining variance in commitment. So let's have a look at that in Jamovi. Back to our example. So I'm just going to run another regression analysis. So as before, we've got commitment as our dependent variable, identification as our covariate, but also now we want to add annual salary, job satisfaction, and age as covariates too. We want sex to be in the model as well, so we're adding it as a factor because that's a categorical predictor. Okay. Again, I want the overall F test, the ANOVA test, and I want the adjusted R squared. I also want the confidence intervals for the correlation coefficient and the beta coefficient as well. Okay. So, key aspects of the output. So it looks like from the adjusted R squared that the model is explaining around about 46.5% of the variance in commitment, the outcome variable. The overall model is significant, so that's our F ratio, degrees of freedom, and the p-value. And then turning to the coefficients table, it looks like identification, even when controlling for all of these other predictors, identification is still a positive predictor. And when we say positive, we mean that as it goes up, the outcome variable commitment also tends to go up, and it's still highly significant. Okay. In terms of the other predictors, it looks like salary and job satisfaction are also significant and positive predictors of commitment. So as both go up, then commitment also tends to go up as well, and those slopes are significantly different from zero. In contrast, our two demographic variables, age and sex, don't seem to be associated with. They don't seem to predict variation in commitment. Okay, non-significant. All right. So I just want to emphasize what the meaning of the coefficients and significance are in multiple regression. So I think possibly the best way of defining it is that each individual coefficient and its significance, its difference from zero, indicates whether an IV, a predictor, explains a unique part of the variance in the DV. In other words, when I say unique part of the variance that is distinct from the parts explained by other predictors in the model. And that is estimated when those other independent variables are held constant, either at their mean value, if it's a continuous predictor, or at the reference category value, if it is a categorical predictor, like sex. Now, the other thing I want to emphasize here in multiple regression in terms of output is the standardized coefficient gives you a basis for comparing the relative strength or importance of individual predictors in the model. So because a standardized coefficient involves turning all of the variables into using the same metric, as it were, standardizing them, it means they all have a mean of 0 and they all have a standard deviation of 1. It means that they are then comparable with one another. So overall, we can look at a set of beta values in a regression model, standardized coefficients in a regression model, and judge which of these is the strongest predictor of the outcome variable. In this case, the beta of identification is 0.39, which is larger than any of the others. So although this doesn't give you an actual test of the relative strength of these coefficients or the roles of these predictors, descriptively at least, it suggests that identification is the strongest predictor in the model of commitment, followed by job satisfaction, followed by annual salary. Okay, so the beta coefficient gives you a basis for comparing the relative role of individual predictors in the model. Okay, now last thing we're going to do in this session is throw what might be a little bit of a curveball. I'm going to do the same analysis again, but actually using analysis of variance, general linear model. So I'm going to go back to Jamovi, and rather than running the analysis through regression, I'm going to go to linear models and general linear model. This is what I used for between participants ANOVA. Okay. So in this, I'm going to enter again, commitment is our dependent variable. We have sex as a factor and annual salary, identification, job satisfaction, and age as covariates. Okay. Now, if I scoot back to the slides, we'll zoom in on the output. Now, the key thing I want to highlight here is you get exactly the same outcomes. So the R squared values of the model, the ANOVA model, are exactly the same as the r-squared values in the regression model. The p-values are identical, and the f ratios are also have a direct relationship with t. So the f ratio in this ANOVA table is simply the t statistic from the regression table squared. Okay, so the output is pretty much exactly the same, or you could draw very similar conclusions. In fact, just to take it one step further, I'm going to go back to Jamovi. Okay, this is our ANOVA output table. I'm just going to go back up to the regression model that we just ran. And I'm going to tick this one extra box here, omnibus test, ANOVA test. And what that does is it gives us an ANOVA table. And that ANOVA table in the regression output, for where we look at the effects of each individual predictor, is pretty much identical with the results of the actual ANOVA that we just ran. Okay, so our sums of squares, our f ratios, and our p-values. Okay, it's exactly the same. So why is that? Okay, well, it's basically because analysis of variance and multiple regression are both versions of the general linear model approach to analysis. Analysis of variance, as we've been doing it, is effectively regression. They are functionally the same thing, okay, and vice versa. And the implication of this is that pretty much any linear multiple regression analysis can in principle be done in an ANOVA, and vice versa. Anything you can do in an ANOVA, mostly, can be done in a multiple regression analysis too. So why do we run analyses of variance for, say, categorical predictors versus regression for continuous predictors? Well, actually, the reason for selecting one approach over the other, going the ANOVA route rather than the regression route, is, for me personally at least, simply a pragmatic choice based on the ease with which I can extract particular bits of information from the output for a given test. Okay, but in principle, yeah, they are functionally equivalent. ANOVA and regression are pretty much the same thing. Okay, so whenever we think of that rule of thumb that I suggested in the first lecture in this series, where if we have categorical predictors we do ANOVA and continuous predictors we do regression, that's why that's not a law, it's simply a rule of thumb based on practical considerations rather than any actual substantive difference in principle between ANOVA and regression. Okay. All right, I'll leave it there for this session. Next time round, I'll pick up again on regression. I'll go into a little bit more depth and extend on other types of regression analyses, looking at hierarchical and possibly exploratory regression, and looking at how we deal with categorical predictors, and then finally moving into cross-lagged analyses, cross-lagged regression analyses as a way of maybe trying to grapple with causality in longitudinal survey designs. All right, thanks very much in the meantime for watching, and take care, and see you next time.